In numerical methods too, we will see the second method, Euler's method of solving a linear differential equation of first order. Okay, so for that I consider a linear differential equation of first order whose general equation is dy by dx is equal to f of x comma y with an initial conditions y of x naught is equal to y naught. So this is an initial condition, y of x naught is equal to y naught. We know the solution of this differential equation is y is equal to y of x. We know how to solve a differential equation of first order by separation of variables and reducible to separable form, homogeneous equation, reducible to homogeneous equation, linear equation, and reducible to linear equations. We have seen the different methods of solving a linear differential equation of first order. So whose solutions may be expressed as y is equal to y of x ಅಂತ express ಮಾಡಿರ್ತೀವಿ. So ಅದರ 6 different methods solve ಮಾಡಿ ಅಲ್ಲಿ y is equal to y of x ಅಂತ express ಮಾಡಿರ್ತೀವಿ. So here we draw the curve to this equation. ಈ equations ಗೆ ನಾವು curve ಅನ್ನು draw ಮಾಡ್ತಾ ಇದೀನಿ. The curve is drawn to this equation is shown in this figure. The aim of the Euler's method is to find the ordinate of any point on this curve. ಈ curve ಮೇಲೆ, suppose here is a q, I find out this q. Q is any point on this curve. I require to know what is the ordinate of this point. What is the ordinate? Ordinate means y value ಏನು ಅಂತ ಕಂಡುಹಿಡಿಯಬೇಕು. Okay, what is y value? So this is x and this is y value. What is y value? We require to find. That is our aim. Okay, for that I made a construction like this. This is the curve I drawn this. So y of this is the point. I call this point is x. Y of x naught is equal to y naught. This is y of x naught is equal to y naught, or in this point we call x naught y naught. So this is the boundary value of the function, value of the differential equation dy by dx is equal to f of x comma y. I draw a tangent at this point. This point. This is the tangential line. This is the tangent. Again, I draw a line. I'll draw a line joining this point, joining the curve at q. I draw a line which meets the curve at q, which passes through at x naught y naught. Okay, so we require to know what is the ordinate of this point q on this curve. Ordinate of this point q on this curve. Actually, the tangent drawn to this curve is here. This is the point. Exactly. If you draw the extended like this, this is the curve. I extend the same lines to this point q, and this is Pn. I extend a tangent. While solving the equation, we obtain this value. Approximation value is this. And actually true value is where this extended line meets the point q. This is the true value of yn. The difference between approximate and true value is this is the error. Okay. So I made a construction like this. The tangent, I divide the tangent into n partitions. I made the tangent into n number of divisions with a width of h. This is h, equal widths, n number of divisions. I call this point as L, L1, L2, continuous Ln. Okay, this is x naught, and x naught plus h becomes x naught plus h. This is the point, x naught plus h, x naught plus 2h, and obviously this is x naught plus nh. This point is x naught plus nh because we have divided this into n number of partitions. Okay, this point is P. I call this is a point P. This point is P, P1, P2, this point is P2, P3, like this. This is Pn. Okay, and you join this, draw the perpendicular from P to another partition P2 where it meets, I call it R1, and this is R2, this is R2, and similarly continues, this is Rn. Okay, so this is all the construction I made, and now I consider for our finding the initial value of this, I consider this proportion, this portion, and enlarged view will be here. I written this enlarged view with this. P is, see here the point P, R1, P1, and this is the angle made by theta, and we require to know the initial approximation or the first approximation, that is y1. This length is y1, okay, and this is y0. Okay, so what is tan theta in this figure? So this is what I already told you. They divide the curve into a number of equal parts with a width h. The tangent at P is approximated as tan theta is equal to. The tangent at P is approximated as tan theta is equal to P1 R1 divided by P R1, opposite by adjacent. Okay, so that is P1 R1 by P R1. So we know how to expand, how to write this distance minus this distance, P1 L1 minus R1 L1, it gives this P1 R1, that is y1 minus y0. We know this is y1, this length is y1 minus y0 gives PR1. y1 minus y0 gives P1 R1, I'm sorry, P1 R1. So that is y1 minus y0, and the difference, this L1 minus L. The L1 is x0 plus h minus x0. x0 goes and remain is h. So we know this tan theta is equal to, it is the f dy by dx at x0 y0. dy by dx at x0 y0. x0 y0, and that value is f of x0 y0. So y1 minus y0 by h, this is simplification, and we require to know what is y1. y1 is equal to, cross multiply this and transform y1 to this, y0 to this side, and y1 is equal to y0 plus h into f of x0 y0. So this is the initial, this is the ordinate of the point, P1, on this curve. Similarly, we generalize for the P2. What is the ordinate at P2? We require to know what is y2. Alright? We require to know what is y2. So for that, the tangent at P2 is approximated as tan theta 1 is equal to, that is P2 R2 divided by P1 R2, opposite by adjacent. We know this is f of x1 y1 is equal to, we know similarly we repeat the same process, we've done the same process, y2 minus y1 divided by h, and y2 is equal to, multiply this to h, and y1 plus h into f of x1 y1. Similarly, inducing on the same way, the tangent at Pn, the tangent at Pn is approximated as yn is equal to, it is yn minus 1 plus h into one lesser value, yn minus 1 plus h into f of xn minus 1 yn minus 1. So this is we call Euler's formula to find ordinate of a point Q on the curve, the given curve, the solution curve y is equal to y of x. Okay, this is the Euler formula. This is how we find the ordinate of the point, any point on the curve, by using Euler's method. Thank you for watching the video.